Earth had 2 moons once. This isn't speculation. The evidence is sitting on the far side of the moon right now, a layer of crust 30 kilometers thicker than it should be, the quiet bruise of a collision 4.4 billion years ago. We are going to imagine what life under 2 moons would have been like. The tides, the light, the slow rhythm of nights that never fully darken, the mythologies that might have grown around a sky that does not match our own. Somewhere near the middle of this story, we are going to tell you the part most people never hear. We're going to walk you back slowly from imagination into geology. Because the question, what if Earth had 2 moons, turns out to be older than it sounds, older than humans, older than oceans, older than the very first single-celled life clinging to a warm, restless seafloor. For most of this video, you are going to drift between 2 worlds. One is the world that might have been if the sky above you tonight had 2 pale faces instead of 1. The other is the world that actually was, for perhaps 100 million years, in a time before there was anyone left to remember. Both worlds are real in their own way. One lives only in equations and simulation. The other lives in the rocks above us, in the asymmetry of every full moon you have ever seen, and in a stillness that has been waiting 4.4 billion years to be noticed. There is no rush tonight. There are no diagrams to follow, no calculations to keep up with. There is only a long, quiet walk through a piece of cosmic history that almost no one talks about. Let your shoulders settle. Let your breathing slow, and let the sky, the one above you and the ones that might have been, drift past you in their own time. Before we imagine a second moon, let us spend a few moments with the only one we have. Tonight, somewhere over your head, perhaps hidden by a roof, perhaps behind a low bank of cloud, perhaps cut sharply against a deep indigo sky, there is a moon. It is roughly 3,474 kilometers across, about a quarter the width of Earth itself. By the standards of our solar system, extraordinarily large for a body its parent size. Most planets do not have moons this big in proportion to themselves. Most planets, in fact, do not have moons that look anything like our moon at all. It is a strange and lucky thing that we have one, and that we have only one. That single moon does more than light our nights. It is, in a quiet way, one of the architects of life on Earth. Its gravity pulls a slow, twice-daily breath into our oceans. The tide rises and falls, a movement so familiar that we forget what an extraordinary mechanical fact it is. Trillions of tons of water, lifted gently against gravity, twice every Earth day, by a body almost 400,000 kilometers away. Tide pools form, estuaries flush themselves clean. Whole categories of life, barnacles, periwinkles, certain crabs, certain seabirds, certain ancient lineages of fish, have organized their entire existence around the rhythm of those tides. Without the moon, none of them, exactly as they are, would exist. Locked in a patient orbit 250,000 miles away, also stabilizes the tilt of our planet. Earth's axis is currently inclined about 23.5 degrees from the vertical. That tilt gives us seasons. It gives us spring rains and autumn leaves and the long, slow migration of birds across hemispheres. Without the moon, that tilt would not be steady. It would wander. Climate models suggest that without the moon's stabilizing pull, our axial inclination could swing from near zero to nearly 90 degrees over millions of years. The poles could become the tropics. Whole continents could pass through climatic chaos that would make the building of any complex civilization, perhaps even of complex life itself, almost impossible. And there is the slow, almost imperceptible work the moon has done on Earth's rotation. When the moon was younger, billions of years ago, our day was much shorter, perhaps as short as 5 or 6 hours. Dragging on the oceans through its gravity has slowed Earth's spin gradually over deep time, lengthening our day to its current 24 hours. In another billion years, the day will be longer still. This is what one moon does quietly while we sleep beneath it. Now, gently, imagine that there are two. Imagine, in the same sky, in the same indigo evening, in the same quiet street, where your only sound is the distant hush of wind in the trees, that there is a second moon. Not a star, not a planet. A second moon. It is smaller than the one you know, perhaps 1,000 kilometers across, less than a third the width of our own. It does not dominate the sky. It is not blinding. From your standpoint on the ground, it looks like a coin held at arm's length, faintly glowing, faintly textured, drifting along its own path. Tonight, in this imagined sky, the larger moon is rising in the east. It is the same moon you know, pale, scarred, 3/4 full. As the larger moon climbs, the smaller one follows it, perhaps half an hour behind, perhaps an hour, perhaps more, depending on the orbit you give it. Or perhaps the smaller one rises in a completely different part of the sky, on a path inclined to the larger moon's orbit by 10 or 20 degrees, climbing diagonally where the larger moon climbs straight. The first thing you notice, standing in this imagined night, is not the second moon itself. The first thing you notice is the light. There is more of it, not double. Light from the smaller moon is not a simple sum. Its surface is smaller, its distance might be slightly different, its phase will rarely match the larger moon's phase exactly. But the night, on average, is brighter than ours. Where our full moon casts shadows sharp enough to read by in open country, the night under two moons would, on most evenings, be even more luminous. The deepest darknesses of our sky, the truly black hours, the moonless nights, would be rare. Perhaps once a month, when both moons reach their new phase together, you would have something like the dark sky we know now. The rest of the time, the night would carry a soft, persistent glow. The second thing you notice is the geometry. Two moons in the sky do not move together. They drift past each other slowly, like two boats in a harbor, sometimes near, sometimes far. Some nights they would line up almost perfectly, the smaller one passing across the larger one's face, a dark coin sliding over a pale one. The sky would briefly hold an eclipse you could not have on Earth, a moon crossing in front of another moon, the geometry of three bodies, sun, moon, second moon, playing out above your head every few weeks. On other nights, the two moons would stand on opposite sides of the sky, like two unmatched lanterns, one rising as the other sets. There would be moments in such nights when the entire sky was bright above you, with no true horizon left in shadow. There would be other moments when both moons gathered low in the same quadrant, and the rest of the sky stretched away into a darkness that felt deeper by contrast. You would notice after some time that the smaller moon moved differently. Because it is smaller, and because we will assume it sits closer to Earth, its orbit is faster. It might cross the sky from one horizon to the other in just a few hours. The larger moon, our familiar moon, takes most of a night. The smaller one, in this imagined world, would race past it, catching up, passing, drifting ahead, a slower star with intent, threading the deeper rhythm of the larger moon's path. You would learn, very quickly, the names of two new lights. You would learn their phases. You would learn the days when they were full together, and the days when one was a thin sliver while the other was a perfect disk. There would be a calendar in two voices, a poetry perhaps of two faces. When you had grown accustomed to the look of the sky, you would step down to the shore and meet the tides. The tides are the first place where having two moons stops being beautiful and starts being strange. Tides on our Earth are, fundamentally, a deformation. The moon's gravity pulls on Earth more strongly on the side facing it than on the side facing away. This pull stretches the planet very slightly into the shape of a faint, slow water and rock football. The two bulges, one on the moon-facing side, one on the opposite side, are what we feel as high tides, Earth rotates beneath those bulges every 24 hours, which is why each shoreline experiences 2 highs and 2 lows per day. The sun adds its own smaller pull, about half the strength of the moon's tidal effect. When the sun and moon align, at full moon and new moon, we get the strongest tides, called spring tides. When they pull at right angles, at first quarter and third quarter, the tides weaken into what we call neap tides. This is the rhythm we know. 2 highs, 2 lows, modulated by the sun, repeating with a steady ancient patience. Now, gently, add a second moon. The new moon, our smaller companion, also pulls on Earth's water. It also raises a bulge, a smaller bulge, because the moon itself is smaller, but a real bulge nonetheless, and it raises that bulge along its own line of sight, which, as we said, almost never matches the line of sight to the larger moon. So now, instead of 2 bulges in the ocean, we have something more complicated. We have 1 pair of bulges from the larger moon, slowly turning beneath us as Earth rotates. And we have a second pair of bulges from the smaller moon, turning beneath us at a different rate, along a slightly different axis. The 2 patterns slide past each other constantly. They reinforce each other one moment and partially cancel each other the next. The result is not simply higher tides. The result is a tidal pattern that becomes irregular in a way our oceans today never experience. Some shorelines, in some weeks, would see 4 high tides per Earth day instead of 2. Other shorelines on other weeks would see only 1. Long, slow swell that lasted half a day before draining. The familiar predictability of 2 highs and 2 lows per day, the rhythm that fishermen and seabirds and oyster gatherers have learned over thousands of years, would dissolve into a more shifting pattern. There would still be averages, there would still be cycles, but you could not, simply by looking at a calendar, predict the next high tide of your own coastline without serious calculation. And during the rare moments when both moons aligned with the sun, when all 3 of those gravitational pulls fell along the same line, the tides would be enormous. A typical spring tide is perhaps 50 centimeters higher than an average tide, in some places much more. With a second moon thrown into the alignment, the spring tide could rise dramatically higher. If the second moon were of significant size, the highest tides, the tides of triple alignment, could be several meters higher than anything our planet currently produces. There are scenarios, in some published thought experiments, in which the highest tides under 2 moons reach 8 times the height of a normal tide. Coastal life on a planet with such extremes would not look like coastal life as we know it. Tide pools would be different. The deepest tide pools, the ones that fill at the very highest waters and remain through the lowest, would be vastly larger and more isolated. Whole estuaries would, at their lowest tides, become near deserts of cracked mud, and at their highest, become broad inland seas, reaching kilometers further upstream than they do today. Salt marshes would grow taller, fed by the deeper inundations, and would harbor different communities of plants, species adapted to occasional submersion in meters of salt water rather than centimeters. Migrating fish, the salmon, the eels, the sturgeons of this imagined world, would have to read more complicated tide tables. Their journeys upstream would be timed not to one rhythm, but to 2 interweaving rhythms. Predators that hunt by tide, gulls, certain rays, certain wading birds, would either become more skilled at reading complex patterns or would specialize on one cycle and hunt sparingly. Coral reefs, which depend on stable, predictable water levels for spawning, would adapt to a cycle modulated by both moons and might spawn at different alignments, perhaps in coordinated bursts every few months when the 2-moon geometry briefly resembled the sky their distant ancestors had known. There would also be silences. There would be days on this imagined Earth when the 2 moons happened to pull at right angles to each other and to the sun, days when the tide barely rose and barely fell. The shore, on such days, would be eerily still. The water would lie almost flat against the same line for hours, a quiet that sailors would name and tell stories about. And then, slowly, As the geometry shifted, the tide would begin to breathe again. Coastal cities, were any to exist on this earth, would be built differently. Seawalls would be higher. Foundations would be deeper. Settlements would gather not at the average shoreline, as ours often do, but well above the highest possible alignment tide, meters, perhaps tens of meters, above what looked like the everyday water's edge. Whole categories of architecture would have evolved around the question of where exactly the sea is allowed to reach. But before there are cities, before there are seawalls, before there is anyone to tell stories about the silent days, there is just the slow, complicated breathing of an ocean that has two pulses instead of one. The next thing the second moon would change is the night itself. On our Earth, true darkness is rare and getting rarer. Light pollution from cities has flooded most of the inhabited world with artificial glow. But even where the cities are far away, out in deserts, on mountain peaks, on the long, calm latitudes of open ocean, even there, true darkness comes only in the new moon phase, when our moon is between Earth and Sun, and the night sky has only the stars and the faintly green air glow of the upper atmosphere to light it. Add a second moon, and that kind of night becomes almost impossible. Because the two moons travel on different orbits with different periods, their phases almost never coincide exactly. When the larger moon is new, invisible, lost in the glare of the daytime sun, the smaller moon is almost certainly not new. It might be a delicate crescent low on the horizon. It might be a half disk rising at midnight. It might be an unblinking full small moon hanging in the deep night, casting shadows softer and bluer than the ones we are used to. The probability of both moons being simultaneously new, of true deep primordial darkness arriving on the same day, is low. It would happen perhaps once or twice a year in narrow windows that ancient cultures would surely have noticed and named. For all the other nights, there would be moonlight of some kind. Sometimes it would be the steady, familiar light of our own moon, with the smaller moon merely adding a faint secondary glow. Sometimes the smaller moon would be the dominant nightlight, our larger moon hidden below the horizon while the smaller one tracked alone across the stars. Sometimes both would be in the sky at once, and the world below would be touched by two distinct sources of light, casting two distinct sets of shadows, each tree throwing two faint silhouettes onto the ground at slightly different angles. This sounds romantic, and it might be. But for the living world, it would also be a profound disruption. Many animals navigate by moonlight. Sea turtle hatchlings on our Earth find their way to the ocean by following the brightest light on the horizon, which, on a wild beach, is the moon shimmering on the surf. With two moons in the sky, the brightest reflection might lie in two different directions on the same night. Newly hatched turtles in this imagined world might wander in confused arcs, drawn first one way and then the other, never quite reaching the surf. Whole evolutionary lineages would have to have developed alternative cues, perhaps the slope of the sand, perhaps the smell of the salt, long before they could be safely guided by light alone. Coral reefs on our Earth often spawn on a precise lunar trigger. A particular coral species on a particular reef will release its eggs and sperm into the water within a window of a few hours on a single night, during a particular phase of the moon in a particular month of the year. The synchronization is extraordinary. Millions of polyps across hundreds of kilometers, all releasing on the same night, so the gametes have the best chance of finding each other in a vast, dark ocean. With two moons signaling at slightly different rhythms, this perfectly tuned trigger would have to be either retuned or fragmented. Some reefs might spawn on the larger moon's calendar. Others might spawn on the smaller moons. Others might wait for the rare alignment nights, when both moons' phases agreed, and release in great pulses every few months. Predators, too, would change. On our Earth, certain hunters preferred dark nights, owls, certain cats, certain nocturnal mammals, because their prey are easier to ambush in low light. Other hunters prefer moonlight, when their own eyes can see more, even if their prey can also. The balance of those strategies, finely tuned over hundreds of millions of years, would settle differently on a planet whose nights were, on average, brighter and more variable. And humans, if there were humans here, would sleep differently. Our own circadian rhythms are tuned not only to the sun, but more subtly, to the moon. Studies have shown that human sleep is, even today, slightly shorter and lighter on the nights leading up to a full moon, even when we are indoors, in artificially lit rooms with curtains drawn. We are, somewhere deep in our nervous systems, still aware of the lunar cycle. With 2 moons, that awareness would split. There would be doubled cycles, longer cycles, broken cycles. There might be people on this imagined Earth who slept best on the rare doubly dark nights, people who organize their important rest around the geometry of 2 distant lights, the way some today organize their lives around the seasons. Sleep might be more communal, more scheduled. Long, deep sleep might be a precious, ritualized thing. There would be on this Earth fewer truly black skies. There would be fewer hours of perfect darkness in any given year. The Milky Way, which on our world stretches in a broad, soft band across truly dark nights, would here be visible only on the rarest occasions, and seeing it would be a once-a-year astonishment. Stargazers would build observatories at higher altitudes. Astronomers would work in narrow seasonal windows. Whole civilizations might consider the Milky Way as sacred, a thing that comes out only when the 2 great lights are simultaneously asleep. But long before observatories, before turtles, before reefs, before the species we know, long before any of that, the 2 moons would still be there, alone with the early ocean, pulling at it, lighting its waves with 2 pale faces, setting its rhythms in a more complicated music than our world has ever heard. If 2 moons changed the tides and the nights, they would also change something even more fundamental. They would change time itself as humans measure it. Our calendar is a piece of inherited compromise. We have a year, which is the orbit of Earth around the sun, and which lasts about 365.25 days. We have a day, which is the rotation of Earth on its axis. And we have a month, which is, almost everywhere in human history, derived from the cycle of the moon, the time from one full moon to the next, which is about 29.5 days. The whole structure of our weeks, our festivals, our agricultural rhythms, our religious observances has been built, layered, adjusted, and rebuilt around these 3 numbers. Now place a second moon in the sky. The smaller moon, in our imagined scenario, is closer than the larger. Its orbit is therefore faster. Its phases, new, crescent, half, full, back to new, would complete in much less time than the larger moon's 29.5 days. Perhaps the smaller moon's cycle would be 10 days, perhaps 15. The exact number does not matter for our purposes. What matters is that it would be different. 2 distinct lunar months would unfold simultaneously in the same sky. This would not be a problem exactly. It would simply be a fact. Cultures on this Earth would have grown up with it, the way ours grew up knowing that the sun moves one way and the constellations slowly drift another. But it would change everything about how time was kept. Consider how different cultures count time on our Earth. Some traditions are solar, built around the year, the seasons, the harvest. Others are lunar, built around the cycle of the moon, regardless of where the seasons fall. Still others are lunisolar, weaving both rhythms together with extra months added in certain years to keep them aligned. The Hebrew calendar, the traditional Chinese calendar, the Hindu and Buddhist calendars, the Islamic calendar, each of these has, over centuries, found a different solution to the puzzle of 2 natural rhythms that almost, but not quite, fit together. On a 2-moon Earth, that puzzle becomes a triple braid. You have the year, set by the sun. You have 1 lunar month, set by the larger moon, perhaps about 29 days like ours. You have a second lunar month, set by the smaller moon, perhaps about 10 or 12 days. None of these 3 numbers divides evenly into the others. None of them aligns. You would have to braid all three together, not pair them, but braid them. Every culture's calendar would, almost by necessity, be more elaborate than any calendar that has ever existed on our world. Every culture's mythology would, almost by necessity, give significance to alignments, the days when both lunar months reach the same phase together, the years when those alignments fell on a particular season of the sun. The religious imagination of such a planet would, one suspects, be richer than ours in certain dimensions. The poetry of two moons rising, the poetry even more of two moons setting, is not poetry our world has ever needed to invent. Songs would exist about the patient, slow dance of the great moon and the swift small moon. Festivals would gather around the rare nights of double full, when both lunar disks hung at their brightest in the same quiet sky. Other festivals would mark the rarer nights of double new, when the world was as dark as it ever became, and the Milky Way returned in its full ancient brightness. There would perhaps be twin gods. Almost every culture on our earth has imagined the moon as a single deity, sometimes male, sometimes female, sometimes both, sometimes neither, but always single, always one face. On a two-moon Earth, the imagination would split. There would be a great moon, slow, patient, the rhythm keeper, and a smaller, quicker companion, perhaps a child, perhaps a sibling, perhaps a friend, perhaps a rival. Some cultures would describe them as lovers, eternally chasing each other. Some would describe them as twins playing a long game. Some would describe them as enemies whose paths sometimes crossed in catastrophe. The eclipses in particular, the moments when the smaller moon passed across the larger, would be the rawest material in the world for myth. The week itself, that strange 7-day unit which has no astronomical basis on our Earth and which we owe to ancient traditions of planetary symbolism, might never have arisen. It might have been replaced, on this imagined Earth, by a unit drawn from the smaller moon's quarter cycle. The week might be 3 days. It might be 4. It might shift across cultures in the same way the calendar does, with each tradition choosing a unit that suited its own tides, its own harvests, its own gods. Naming would be different. We have in our oldest poetry a few names for the moon, the silver, the pale lantern, the lady, the watcher. On a two-moon Earth, every culture would have at least double the lunar vocabulary. There would be names for the larger moon at every phase, and parallel names for the smaller moon at every phase, and additional names for their alignments and oppositions. Storytellers would have richer material, children would learn longer rhymes, and astronomers, when they finally arose, would have a head start. They would have learned, simply by watching the sky, that the heavens were full of motion, full of bodies in unequal orbits, full of the small, steady tug of war that determines what we call gravity. The discoveries that took our scientists, on our Earth, centuries of patient observation, the laws of orbital motion, the inverse square pull of mass, the slow precession of a stable system, might have come a century or two earlier on a planet where the evidence was nightly, visible, and impossible to ignore. It is curious to think that two moons might have given us, by simple accident of geometry, an earlier physics. But of course, before there are any of these things, before names, before festivals, before astronomers, there is only the question of whether two moons can survive each other for long enough to matter. Two moons in orbit around the same planet are not, mechanically speaking, the same as two children sharing a swing. They do not simply swing past each other and continue, undisturbed on their separate arcs. Each one feels the other's gravity. Each one is, in some quiet way, pulling the others slightly off course. For a long time, astronomers wondered whether two large moons could ever orbit a single planet stably. The intuition was that they should disturb each other so persistently, on such long timescales, that one or the other would eventually be flung loose, or sent inward to crash, or jostled into a wild, eccentric orbit that no longer fit the planet's gravitational well. Modern simulations have softened that intuition. The truth, as is often the case in orbital mechanics, depends on the details. Two moons in well-separated prograde orbits, with low relative inclinations, with masses small enough that neither one dominates, can in fact remain stable for extraordinarily long periods. The key word is resonance. If two moons fall into a resonant relationship where their orbital periods stand in a simple ratio, 2:1, 3:2, 4:3, then the gravitational nudges they give each other tend to repeat at the same points in their orbits. Those repeating nudges, instead of accumulating into chaos, balance themselves out. The moons settle into a long, patient choreography. They orbit and orbit and orbit for 1 billion years undisturbed. The moons of Jupiter dance this way, and Ganymede are locked in a resonance so precise that for every 4 orbits Io completes, Europa completes 2 and Ganymede 1. The pattern has held for hundreds of millions of years, so it is not impossible. A planet with care can keep 2 moons, or 3, or for that matter more. But the keeping is not free. Each moon, as it raises tides on its parent planet, also feels a tide raised on itself. That mutual tidal interaction over deep time transfers angular momentum from the planet to the moon. The moon, gaining angular momentum, drifts slowly outward. The planet, losing it, slows its rotation. This is the process that has, on our Earth, lengthened our day from a few hours to 24, and pushed our moon outward from an early orbit, perhaps 15 or 20,000 kilometers above the surface, to its current distance of 384,000 kilometers. With 2 moons, this process is doubled. Or rather, it is more than doubled, because the moons interact with each other as well as with the planet. Tidal dissipation accelerates, the day lengthens faster, the moons drift outward more quickly, and the gravitational dance between the 2 moons, while stable in the short term, is never perfectly so. There is always some slow drift, some long oscillation, some accumulating perturbation. The 2 moons cannot, on geological timescales, ignore each other. If they sit close together in their orbits, the perturbations are stronger and the relationship is more fragile. If they sit far apart, the perturbations are weaker, but never zero. Sooner or later, on timescales of hundreds of millions of years to a few billion, something has to give. There are, mechanically, 3 ways for a 2-moon system to end. The first is collision. The smaller moon, perturbed by gravitational interactions, drifts onto an orbit that crosses the larger moons. The result is a slow merger, or a violent shattering, or, in some specific configurations, an oddly gentle accretion in which one moon ends up plastered onto the other. We will return to this scenario shortly. The second is ejection. The smaller moon, accelerating through resonance interactions, gains enough velocity to escape the planet's gravity entirely. It is flung loose into solar orbit, perhaps eventually colliding with another planet, perhaps captured by another, perhaps ending up adrift in the asteroid belt, or in a wide, wandering arc through the outer solar system. The planet keeps its larger moon. The smaller one becomes, in time, just another small body of the inner solar system, a quiet wanderer with a forgotten origin. The third is infall. The smaller moon, losing angular momentum to tides or to encounters with the larger moon, drifts inward instead of outward. It approaches the planet's Roche limit, the distance inside of which a moon's own gravity can no longer hold it together against tidal forces. Inside the Roche limit, the moon disintegrates. Its pieces become a ring around the planet. The planet, for a time, has rings instead of a smaller moon. Eventually, those rings, too, slow under the influence of tides and rain down onto the planet's surface or accrete back into a smaller body, or are simply lost. Each of these endings has happened somewhere in the solar system. We have evidence of each. The rings of Saturn, in particular, are widely thought to be the dismembered remains of a moon that drifted inward. The asteroid belt contains bodies that may, by some hypotheses, be wanderers ejected from earlier moon systems. And on the moon itself, on the side we never see, lies what may be the geological signature of a slow, gentle, accretionary collision 4.4 billion years ago. In every case, two moons does not last forever. Or rather, it does not last as two. The mathematics of orbital mechanics, given enough time, forces a reduction. Either the moons merge, or one is lost, or one disintegrates. The end state is almost always a single moon, larger and more massive than either of the originals, plus perhaps some scattered debris. Which is to say, a planet can have two moons, but not, on the deep timescales of its own existence, comfortably. Two moons is a phase, a long phase perhaps, a phase lasting tens of millions or hundreds of millions of years, but still, in cosmic terms, transient. The default state of a planet is one large moon, one small moon, no moons or rings. Two moons of similar size in stable orbit is a rare, fleeting thing. This is the first hint in everything we have said so far that the question of two moons is not just a thought experiment. It is a question about a kind of system that, if it exists, must end. Which means, somewhere in the universe, every two-moon planet is either still in its phase or has already passed through it. And our Earth, 4.4 billion years ago, may have been one of them. Gently set down the imagined Earth and pick up the real one. Everything we have walked through, the second moon rising over the indigo evening, the doubled tides, the brighter nights, the longer calendars, the eclipses where one moon crosses another, the slow geometry of orbital stability. All of it has been, until this moment, speculation, a thought experiment, a what if, but there is a quiet line of evidence, gathered slowly over the last 50 years, that the what if is not entirely a thought experiment. The line is incomplete. The line is contested. The line is one of several competing hypotheses for a problem that has bothered planetary scientists since the first images of the moon's far side reached Earth. The problem is this. The moon has two faces. We know one of those faces well. The near side of the moon, the side that faces Earth, is the side every human being who has ever lived until 1959 has ever seen. It is the face of all our myths, all our songs, all our paintings. It is dominated by the Maria, the dark patches we sometimes call the seas. The Maria are flat plains of cooled basalt. They erupted from the lunar interior billions of years ago and pooled in great lowland basins. They are smooth, dark, and relatively young, by lunar standards, perhaps 3 to 4 billion years old. The near side of the moon, taken as a whole, is low in elevation, thin in crust, and crowded with these dark, level plains. The far side, the side we never see from Earth, is something else entirely. A Soviet probe called Luna 3 sent back the first images of the lunar far side. The pictures were grainy, low contrast, technically poor by modern standards, but they showed something that startled planetary scientists at the time and has continued to puzzle their successors. The far side of the moon does not look like the near side. The far side has almost no Maria. Smooth basalt plains that dominate the side facing us are mostly absent on the side facing away. Instead, the far side is rugged. It is heavily cratered. It is, on average, several kilometers higher in elevation than the near side. Its crust is much thicker, 30, 40, in places 50 kilometers thicker than the crust on the near side. The moon, in other words, is asymmetric. It is heavy on one side and light on the other. It is high on one side and low on the other. It is bright and rugged on one side and dark and flat on the other. And the asymmetry is so consistent, so global, so striking that it cannot be a coincidence. This is the lunar dichotomy. It is one of the great open questions in planetary science. Several hypotheses have been proposed to explain it, perhaps tidal heating from Earth when the moon was much closer in its early history, caused magma to flow preferentially to one hemisphere. Perhaps a giant impact on the near side excavated material that was then redistributed. Perhaps differences in radioactive heating between the two hemispheres caused different amounts of melting and crustal formation. But in 2011, two planetary scientists, Martin Jutzi at the University of Bern in Switzerland and Jutzi Asphaug at the University of California in Santa Cruz, published in the journal Nature a different hypothesis, a simpler one, a more striking one. They proposed that the moon's asymmetry exists because the moon, for perhaps the first 100 million years of its existence, was not alone. The moon, they suggested, had a companion, a smaller moon, about 1/30th the mass of our moon, perhaps 1,000 kilometers across. It shared the moon's orbit around Earth, locked in a stable Lagrange point 60 degrees ahead of, or behind, the moon. It traveled in convoy with the moon for an unknown but probably long stretch of geological time, and then, somewhere along the way, it fell out of that stable point. It drifted across the gap, it collided with the moon, and it left, on the far side of the moon, the asymmetric crust we still see today. Earth, in this picture, did once have two moons, not for a year, not for a decade, for perhaps 100 million years, and then it had only one. The story is so quiet, so geological, so distant from any human scale that it is easy to walk past. But if Jutzi and Asphaug are right, every full moon you have ever seen has carried, hidden on its far side, the body of another moon. Older than oceans, older than life, older than almost anything we know. Let us tell that story slowly. The story begins, as so many planetary stories do, with a collision. About 4.5 billion years ago, the inner solar system was a more violent place than it is now. The 8 planets of our modern solar system were not yet quite assembled. There were dozens of bodies, ranging in size from boulders to small planets, jostling for orbits in the inner solar system. They collided, they merged, they scattered each other into wider orbits or destroyed each other in single catastrophic encounters. One of those bodies, a Mars-sized object that planetary scientists call Theia, after the Greek Titan who was the mother of the moon goddess Selene, found itself on a collision course with the proto-Earth. Some hypotheses suggest Theia did not approach from far away. It had been sharing the proto-Earth's orbit, locked at one of the stable Lagrange points, perhaps for tens of millions of years, until gravitational perturbations finally disturbed its stable position and sent it inward. Either way, Theia struck. The collision was, by any standard, enormous. It is sometimes called the Big Splash. Most of Theia's mass was absorbed into Earth. Some fraction of both Theia's and Earth's outer material was launched into orbit. That ejected material, hot vaporized rock and dust, gradually cooled and accreted into a single body, our moon. This is the giant impact hypothesis, the dominant scientific explanation for the moon's existence. There are minority alternatives, but the giant impact framework explains a great deal of the chemistry, the angular momentum, the iron content, and the orbital dynamics of the Earth-Moon system. Most planetary scientists accept it. What is less commonly known is that several recent simulations of the giant impact, simulations sophisticated enough to track the details of the post-impact debris cloud, suggest that the cloud may not have collapsed into a single moon. It may have collapsed into more than one. In some simulations, 2 distinct moons form. They form quickly, in a matter of hours, as the hot debris cloud cools and gravity pulls clumps of vaporized rock together. The larger one is what we now call the moon. The smaller one is something else, something less famous, something with no surviving name. The smaller moon, in these simulations, settles into a particular kind of orbit. It does not orbit Earth on its own path, separate from the moon's path. It shares the moon's path. It sits at one of the gravitationally stable points 60 degrees ahead of or behind the moon, the L4 or L5 Lagrange points of the Earth-Moon system. A Lagrange point is a quiet place. It is a location in space where the gravitational pulls of two larger bodies, in this case Earth and the Moon, balance the centrifugal force of the orbiting smaller body so precisely that the smaller body can sit there in stable equilibrium indefinitely. Trojan asteroids of Jupiter occupy similar points along Jupiter's orbit around the Sun. Trojan moons of larger moons can, in principle, occupy similar points along their parent moon's orbit around its planet. So in this picture, our early moon had a Trojan companion. It traveled in formation with the moon. From the surface of the Earth, if any Earth surface had then been habitable, the Trojan moon would have been visible most nights as a smaller, dimmer light, 60 degrees behind or ahead of the larger moon, moving in lockstep with it. Two moons in the sky, not orbiting independently, locked in choreography. For perhaps tens of millions of years, perhaps 100 million years, this is the sky Earth had. And then, slowly, that sky began to change. The reason it changed is itself a story. The moon, as we said, drifts outward over time, gaining angular momentum from Earth's rotation through tidal interactions. The Trojan companion, sitting at a Lagrange point 60 degrees away, drifts outward with the moon. The two-body Lagrange equilibrium is preserved, most of the time. But the moon's outward drift, on the timescale of tens of millions of years, slowly destabilizes the Lagrange point. The point's stability depends on the masses of the bodies and on the eccentricities and inclinations of their orbits. As the moon migrates outward, as Earth's rotation slows, as gravitational perturbations from the Sun and from Venus and from Mars accumulate, the Trojan companion's quiet residence becomes less quiet. It begins slowly to oscillate. The oscillations grow. Eventually, the companion drifts out of its stable point altogether. When that happens, when the smaller moon escapes the Lagrange point, it begins a slow journey toward the larger moon, their orbits no longer locked together. The smaller moon, now drifting on its own, gradually closes the gap. The closing takes time. We are still talking about gravitational dynamics on the scale of hundreds of thousands of years. The smaller moon does not race toward the larger one. It approaches, it loops past, it loops around. The Earth-Moon system, for a long stretch of geological time, contains a chaotic dance in which one moon is gradually, inexorably falling toward the other. And then, after enough orbits, the closing brings the two moons together. What happens next is not a hammer blow. It is something stranger. The collision between the moon and its Trojan companion was, by any standard the universe normally uses, almost gentle. We are accustomed to picturing planetary impacts as cataclysms. The asteroid that ended the dinosaurs struck the Earth at perhaps 20 kilometers per second. The largest impacts in early solar system history, the ones that scarred Mars and Mercury and the icy outer moons, struck at similar or higher speeds. At those velocities, the kinetic energy of the impact is so high that the impacting body and a portion of the surface it strikes is vaporized within seconds. The result is a crater, a bowl-shaped excavation, often hundreds of kilometers wide, surrounded by ejected debris and rimmed by uplifted rock. The shape of the crater is the shape of an explosion frozen into stone. The moon's collision with its Trojan companion was not like this. The two moons, as we said, were drifting toward each other across a destabilized Lagrange point. Their relative velocity, when they finally met, was extraordinarily low. The Jutzi and Asphaug simulations put the impact velocity at perhaps 2.5 kilometers per second, possibly slower. For comparison, that is roughly the speed of a fast bullet, or about a quarter of the speed at which most asteroid impacts occur. It is, in fact, slower than the local sound speed in compressed rock. The collision was, in a strict physical sense, subsonic. A subsonic collision behaves very differently from a supersonic one. When two solid bodies meet at supersonic speeds, the kinetic energy of impact must be absorbed almost instantly, and there's no time for the rock to flow or deform gracefully. The energy goes into vaporization, into shock waves, into explosive ejection of material. The impacting body and a corresponding amount of the target body are essentially shattered and scattered. When two solid bodies meet subsonically, the energy can be absorbed by relatively quiet processes. The rock can flow, the crusts can deform. The smaller body can spread itself across the surface of the larger one, like a wet ball of clay flung gently against a wall, like a slow wave breaking against a cliff. There is no explosion. There is no crater. There is only a redistribution. The smaller body becomes, in effect, a layer plastered onto the larger one. This is what Jutzi and Asphaug simulations show happening between the Moon and its Trojan companion 4.4 billion years ago. The smaller moon approached the larger one over a span of perhaps an hour, growing larger in the larger moon's sky if anyone had been there to see it, swelling until it filled a large portion of the lunar horizon. There was no flash, no shockwave, no thunderous announcement. The two surfaces simply met. The smaller body, traveling at its slow relative velocity, began to spread. Its outer crust, made of materials similar to the larger moon's outer crust, came into contact with the surface of the larger moon. Friction and gravity took over. Over the course of perhaps minutes to hours, the smaller moon was crushed against the larger one's surface. Its rocks, instead of vaporizing, deformed. Instead of fragmenting, they smeared. Instead of excavating, they piled. The simulations suggest that the smaller moon's mass was deposited as a layer covering most of one hemisphere of the larger moon. The layer was thick, several tens of kilometers in places. It covered a region thousands of kilometers across. It changed the shape, the elevation, and the chemistry of that hemisphere permanently. The larger moon, of course, was disturbed by this. Its rotation may have been altered. Its internal structure may have been temporarily reshaped by the gravitational redistribution. But the moon survived. It continued in its orbit. It continued, after some adjustment, in its slow tidal recession from Earth. It continued to face Earth on its own steady cycle. And on the side of the moon that absorbed the collision, the side away from Earth, there was now a region of crust that was substantially thicker, higher, and rougher than the side that had been spared. The Earth, beneath all of this, would have noticed only the slightest change. The combined gravitational pull of the Earth-Moon system did not change. The orbit did not appreciably shift. The tides, the day length, the orbital geometry, all of these continued as they had been. Earth had, simply, lost one of its lights. Where there had been two pale faces in the sky, there was now one. The smaller moon, which had been a dimmer companion 60 degrees ahead of or behind the larger moon, was no longer there. It had become part of the larger moon. Its mass had not vanished. Its memory had not been erased. It had only been absorbed. If there had been any observers, anything at all on Earth capable of noticing, they might have seen the second moon grow brighter and larger over the course of years and centuries as it drifted toward the moon, then approach, then merge in a slow, dim glow, then disappear. They might have seen the larger moon, thereafter, glowing slightly differently for a time, perhaps with a hint of new color from the smear of accreted material, perhaps with a slow change in shape that took thousands of years to settle. But there were no observers. The Earth, 4.4 billion years ago, was a young, hot, partially molten place. Its surface was a sea of magma. Its atmosphere was thick and toxic. Its oceans, if any liquid water existed yet, were forming in the cooler latitudes around the equator. There was no life. There were no eyes. There was, in a real sense, no one to notice that one moon had become a part of another, and that the night sky henceforth would always have a single moon and never two. The collision was witnessed by no one. It happened in silence. It is perhaps the largest single quiet event in the history of our planet's neighborhood. What the collision left behind is what we now call the lunar Farside highlands. The far side of the moon, the hemisphere we never see from Earth, is thick. Its average crustal thickness is perhaps 50 to 60 kilometers, compared to the near side's 30 to 40. That extra material, if Jutzi and Asphaug are right, is the body of the second moon, smeared across the surface of the first. The far side is also high. The mean elevation of the far side is several kilometers above the mean elevation of the near side. The crust there sits on top of the rest of the moon like a lopsided cap. The center of mass of the moon, in fact, is offset from its geometric center by about 2 kilometers, with the offset directed toward Earth because the far side carries more weight than the near side. The far side is heavily cratered, while the near side has been resurfaced by basaltic eruptions over the last 3 billion years, eruptions that have erased much of the early cratering history. The far side has not. The far side carries a record of impacts going back essentially to the moon's formation. It is one of the most heavily cratered terrains in the inner solar system. When you look at images of the lunar far side, you see almost no flat plains. You see crater on top of crater, basin on top of basin, mountain on top of mountain. It is a rugged, ancient landscape, and the far side is asymmetric in chemistry too. The near side Maria are rich in iron, magnesium, and the heat-producing radioactive elements that drove their volcanic eruptions. The far side highlands are different. They are richer in feldspar. They are poor in some of the elements that drove the near side volcanism. The two hemispheres of the moon are, geochemically speaking, distinct. All of this asymmetry has, in conventional explanations, several possible causes. Tidal heating from Earth, when the moon was much closer in its early history, may have melted the near side preferentially. A great impact may have excavated the near side basins. Differences in radioactive heating may have driven different patterns of melt formation. Each of these explanations covers some of the data. None of them, in some scientists' view, covers all of it as elegantly as the collision hypothesis does. If a smaller moon collided gently with the larger one and accreted onto its far side, the resulting layer would be thick. The hemisphere it covered would be high. The chemistry of that hemisphere would be different from the chemistry of the side it did not reach. The crust would be older. The terrain would be rougher. The center of mass of the moon would be offset toward the side that was not augmented. Every major feature of the lunar dichotomy fits in a single explanation: the accretion of a companion. This is why the hypothesis has held attention since 2011, despite remaining a hypothesis rather than a confirmed fact. There are alternative explanations. None of them is decisively ruled out. But the collision hypothesis is perhaps the simplest, the most coherent, the one that requires the fewest separate processes to explain the most features. The full moon you see in the sky tonight is, in a literal sense, asymmetric. You cannot see the asymmetry from Earth. The face that turns toward us is the smoother, lower, thinner crusted half. The far side, the half you have never seen, is the half that, if Jutzi and Asphaug are right, carries the body of the second moon. This means something extraordinary if you let yourself sit with it. Every full moon you have ever looked at has been hiding on its side the remains of another world, not metaphorically, literally. The mountains of the lunar far side are, in this hypothesis, the body of a moon that once shared Earth's sky. The crust is thicker there because something soft and large was pressed into it long ago. The craters there are older because that hemisphere finished forming earlier, while the near side was still being resurfaced by lava. The smear of feldspar-rich material there is the body of the smaller moon, redistributed across thousands of kilometers, no longer recognizable as a moon, but still, in a quiet geological sense, present. When astronauts of the Apollo program brought back samples of lunar rock, those samples came almost entirely from the near side of the moon. The Farside has never been sampled directly by an Apollo crew. Robotic missions have orbited it. The Chinese Chang'e missions in recent years have begun to land on the Farside and study its geology in detail. Future missions will sample the Farside crust. If the crustal samples confirm the chemical signature of the smaller moon, the chemistry of a once separate body, the hypothesis will be largely confirmed. For now, we wait. The Farside keeps its secret in the same way it has kept it for 4 billion years, in plain sight, just out of view from Earth. If you are listening to this in bed, with your eyes closed, drifting toward sleep, picture for a moment the moon overhead. Picture the side that faces you, the familiar pattern of dark and light, the seas you have known since childhood. Now, picture the side you have never seen, the rough side, the side that, in this story, is the grave of another moon, a moon that traveled with our moon for 100 million years before falling silently into it. It is still up there. It has not gone anywhere. There is one more thing to say before we let this story rest. The reason we cannot see the far side of the moon from Earth is that the moon, over billions of years of tidal interaction with our planet, has become tidally locked. Its rotational period exactly matches its orbital period. It turns on its axis once every 27 1/3 days, which is the same time it takes to orbit Earth. The result is that the same hemisphere always faces us. The same face, the same dark seas, the same familiar geography. The other hemisphere has been hidden from human eyes for the entire span of human existence. There is something almost protective in this hiding, as if the moon, in becoming tidally locked, had quietly chosen which side of itself to show us: the smooth side, the peaceful side, the side without the weight of another moon embedded in its crust, the side without the scar. The far side, the side that carries the second moon, has been turned away. Tidal locking happens slowly. It takes hundreds of millions of years of tidal friction to bring a moon into perfect synchronization with its planet. The moon was probably tidally locked relatively early in its history, perhaps within the first billion years after its formation, which means that by the time the second moon collided with the larger one, the locking process was either already underway or had recently finished. The locking determined which side of the moon would always face Earth. It is a curious accident of cosmic history that the side facing Earth is the side without the great accreted layer. If the locking had aligned differently, we might be looking every night at the body of the second moon. We might see its rough, accreted, asymmetric surface. We might see in our familiar full moons an alien geography that we now associate with a place we have never seen. But we do not. We see the smooth side, the side that, in this story, was spared. This is why the story is so easy to overlook. So, the evidence is all on the side we cannot see. The moon's far side is not, for most of human history, a place anyone could study. It was only revealed to us in 1959 when Luna 3 sent back the first photographs. It was only mapped in detail in the 1960s and 1970s by orbital missions of the Apollo era. It was only studied geochemically in the 2000s by orbital spectroscopy. It will only be sampled directly in the coming decades by Chinese, American, European, and other missions yet to fly. The story of the second moon, the story of Earth's quieter, smaller, lost companion, is a story that the universe has kept until very recently behind a curtain. The curtain is the moon itself, turning its smooth face to us and hiding its other face from view. It is only as we have begun to look behind the curtain to send our probes and our cameras and eventually our crews around to the side of the moon we cannot see from Earth that the story has begun to come out. There may be other surprises behind that curtain. There may be evidence we have not yet collected. The far side crust may hold isotopic ratios that confirm or deny the second moon's existence. The deep stratigraphy of the far side highlands may reveal layers that match or do not match Jutzi and Asphaug's predictions. The story will continue to be tested. But what is certain, regardless of which hypothesis ultimately wins, is that the moon you see tonight is older than the human imagination. It is older than the species that named it. It is older, in fact, than the species' ancestors. It has watched Earth pass through the formation of its oceans, the rise of its first single-celled life, the great extinction events, the evolution of forests and dinosaurs and mammals, the slow emergence of consciousness, and the brief recent appearance of the species that finally turned its attention upward and asked questions. If the moon could remember, it would remember being struck once in its youth by a smaller moon that had been its companion. It would remember absorbing that companion in slow silence. It would remember the long, patient cooling that followed. It would remember the slow drift outward from Earth, the slow changes in the tides below, the slow appearance of life on the world it was tied to, the slow rise of cities, the slow brightening of artificial light. It would remember the first probe sent to look at its hidden side. It would remember the footprints left in its dust. The moon does not remember. It is rock. It does not have memory. But the story is recorded in it, all the same. The crust on the far side is the record. The asymmetry is the record. The dichotomy is the record. The moon is, in a literal sense, a written history of its own past, and a piece of that history, perhaps the largest piece, is the body of a second moon that no longer exists as a separate thing. Tonight, when you drift to sleep beneath the sky we have, the sky with one moon and a scattering of stars and the slow, far drift of constellations, you can close your eyes knowing that the sky we have was not always the sky there was. There was a quieter, doubled sky once, in a time, before observers, before language, before mythology, before us. That sky ended in a slow, soft collision 4.4 billion years ago. The sky we live under now is what was left behind. It is, in its own way, the still photograph of a much longer story. A story we are only beginning to read. A story written in the lunar crust, in the asymmetric mountains, in the high old terrain that always faces away from us, in the silence of the far side. If Jutzi and Asphaug, and the others who have followed them are right, ends with the gentlest of all possible endings. Not an explosion, not a shattering. Just one moon settling slowly into another. Two becoming one. The doubled sky becoming the single sky, the lost moon becoming a layer of crust on the surviving moon. The end of one Earth and the beginning of ours. Good night.